my name's Dan, and today I'm going to be walking you through creating a healthcare-based graph in TigerGraph Cloud. So the first thing that we'll need in order to do this is a TigerGraph Cloud account. So you can head over to tgcloud.io and go ahead and create an account if you don't already have one. When creating an account, you will get access to a free tier instance of TigerGraph. This is entirely free. You do not need to enter any payment information or anything like that. You can go ahead and just start using it. So I'm going to go ahead and log in. And then from there, I'm going to head over to the My Solutions tab, and I'm going to click Create Solution. Because we'll be building this graph out from the ground up, we're going to start with a blank solution. We'll scroll down and select Next. We're going to use a free tier instance, so we can just keep all of these settings here default. We can select Next again. Now we'll want to give our solution a name. We're going to be using the Synthea dataset, so I'm going to call this Synthea MedGraph. Tag our solution. This is just a tag so that way we can find it easier on the page if you have a bunch of solutions. If you are really just setting up one solution, you don't have to worry about this, but we could give it a tag anyway. Our initial password will be used to log into our actual TigerGraph Cloud solution. By default, it is TigerGraph all lowercase, and I'm just going to set it as the same thing. There we go. And lastly, we'll want to set our subdomain. This is the actual location that we will use to access our TigerGraph Cloud solution. So this will be the URL that we will go to actually log into our solution. So we'll just call it medgraph. So we'll go to medgraph.i.tgcloud.io. That will be our full address to access the solution later on. We'll select Next, and then we'll just review everything on this page to make sure that it all looks good, and we'll click Submit. I've already created my solution, so I'm going to go back and we'll just switch over to that solution. So that's right here. So after your solution finishes spinning up, you'll see that its status has changed already. It should take between 2 to 5 minutes for your solution to spin up for the first time. And then to actually access that solution, if you wanted to, you click these 4 box icons and select Graph Studio. And that will bring up the Graph Studio interface. This is good to know. This is a great way for us to interact with the graph, but for this demo, we're going to be doing most of our graph interactions from Python. So we'll actually be using this notebook here, this Python notebook, and we'll be connecting through our pyTigerGraph Python connector and building out our graph that way. Let's go ahead and do just that. The first thing that we will need to do is pip install pyTigerGraph. And then from there, we have a couple packages that we need to import. First, pyTigerGraph. JSON is handy just for parsing our JSON outputs from the TigerGraph queries themselves. And we can also include pandas because pyTigerGraph is capable of outputting its results as a pandas data frame. Next, we have some helper functions. These will just allow us to more easily read the results of our queries. And here is where we have our first configuration step. So we'll need to set our connection parameters. And for this initial connection, we will need our hostname, which is the URL of our solution. So that is that link up here, that subdomain that we created with the full .i.tgcloud.io after it. So it would be just this, HTTPS. And then additionally, we need a username and password. By default, the username is TigerGraph, all lowercase, and the password that I set when setting it up was also TigerGraph, all lowercase. So we can go ahead and use those. And we'll see that we've established our connection. Now that we're connected to our TigerGraph solution, we can start thinking about our schema. So this is what our schema will end up looking like. And I know this looks pretty intimidating, but it's not too complicated once we break it down. So the main thing to note here is that this data is based around the Synthea data generator. So if we head over to the page here, we can just see that Synthea is a synthetic patient population generator, and it's based off of real-world data, and it uses that to generate synthetic data that follows real-world models. So that way we can use it to more or less simulate a synthetic population of actual patients. So this was used to generate our data, and it spit out CSV files. And if we head over to this page here, which is this link, the Synthea Data Dictionary, we can see exactly what those files look like and what the table structure of them is as well. So you can check this out to get a good understanding of what the schema will look like. Not all of these fields will be used in our TigerGraph schema, but in terms of what is included in each file, this is a good representation of what our schema will look like. We can see that it contains a list of patients, and related to those patients, we have their encounters with the medical system, and those encounters can be of different types: immunizations, vaccines, shots, things like that, medications, prescriptions, observations, things like an inpatient stay, organizations, those are healthcare organizations, things like hospitals. Providers are people who provide patient care, the people who would work in those hospitals or clinics, and so on and so forth. So these are all healthcare related aspects, and they all tie back to these patients and the ways in which they interact with the healthcare system as a whole. And then another big part of this that really ties a lot of it together is the inclusion of these SNOMED codes. So SNOMED is a way of representing concepts within the healthcare space. To oversimplify, SNOMED is a way of classifying healthcare related topics based on hierarchies to represent their relationships to each other. You can read a bit more about it here, but what you need to know is that a SNOMED code will describe a particular healthcare interaction. So this one is the fracture of a tibia. This one is a code for a medical device, a laparoscope. And this code represents that the situation or the procedure was of emergency priority. So you can see it's a broad range of topics, but there are codes describing more or less all scenarios that you can encounter within a healthcare setting. This section here just breaks down the actual schema of the graph a little bit. This isn't every single vertex, and it's not any of the edges, but it does give a good representation of what is in there and how those vertices are structured. Now that we've talked about the schema, we need to actually create it within our TigerGraph solution. So in order to do that, we're going to use some blocks of GSQL code that we will send to our TigerGraph solution through pyTigerGraph. And those GSQL statements will create our schema. So I'll go through what those look like and how those work and kind of explain what this process looks like. We'll start here with allergies, actually. And if we look at our statement, we first have a create statement. So create just means that we're adding something to our TigerGraph solution. And we can see here that what we are adding is a vertex. And the name of that vertex type is allergies. So we're creating a vertex and it's being called allergies. And then within these parentheses here, we have the primary ID and any attributes that our allergies vertex has. So we'll see here that the first thing we have to declare is that we have a primary ID. And then this next bit here is the name of that primary ID. So our primary ID's name is allergy_ID. And then lastly, we state that that primary ID is of data type string. So primary ID, allergy ID, it is a string. Anything after that primary ID, so we can have stuff after it, or we do not have to. In the case of race here, we just have the primary ID. But if we want to have any attributes on our vertex, we can include those after our primary ID as well. And for those, you only need to specify the name of the attribute and its data type as well. And you can see the list of available data types in our documentation. So that's the basics of how you create a vertex. Now let's take a look at how you create an edge. So edges, one of the things that differs with them is that they can be directed or undirected. A directed edge implies a directional relationship between nodes, something like ownership. So if a person owned a car, that would be a directed edge. The person owns the car. The car does not own the person. So you can really go backwards with that. But one of the complications that having directed edges creates in TigerGraph is that with those directed edges, you can only traverse them in their direction. When you create the edge, you have the option to create a reverse edge alongside of it. So it will effectively create two directional edges in opposite directions that have different names. For the sake of this demo, we're going to be using undirected edges just because it will make our querying a little bit simpler. In the real world, we would probably want to use directed edges here, but for the sake of this demo, I'm going to be simplifying things a little bit just by using undirected edges. So we'll see that we specify undirected, then we specify that it is an edge that we are creating, and that edge's name is patient has attribute. And then the rest of this is also pretty similar to our vertices. We first need to specify the source vertex type that this edge is coming from. So this is coming from our patient vertex type. And then we specify the type of vertex that it's going to. So to our attribute vertex type. Additionally, if we look at this patient has symptom one here, we can see that our edges can have attributes as well. So this edge has the attribute age begin and age end. And you'll see that those are specified exactly like within our vertices, where we specify the attribute name and then its data type. Let's go ahead and just run all these blocks to create our schema within our graph. And we'll just see that as these run, they will just give us some confirmation that they've created those vertex or edge types. And we can see that those are all set. Now what we can do is we can go back into our Graph Studio where we were here before. And if we click on our design schema tag, we will now see that we have a schema. If we did this before, it would have been empty. We can see that our schema has successfully been loaded into our TigerGraph Cloud solution. But the thing to note here is that this schema is in the global perspective. With TigerGraph, you can have a global schema, and then you can propagate that schema down to any graphs that are within your solution. Or you can have those graphs have unique schemas or elements of unique schemas within them. So you could bring in some aspect of the global schema and create some local schema for any particular graph. But for this case, we're just going to create our global schema and then bring the whole thing into the graph that we'll be creating. So the way that we'll do that in pyTigerGraph is, again, another GSQL block that we'll be running. And this one is create graph, and we'll be calling it medgraph. And then what we do here is simply we list the name of every single edge and vertex that we are loading in. We want to include our entire schema. So everything that we created here, we will be loading in to our graph down here. And we can just run this block. And this will take a couple seconds to actually create the graph. So we will let it run. There it is. So our graph is now created. And if we were to head into Graph Studio, we could see, after we refresh the page, we could see that we now have a graph medgraph. And if we go into that graph, we can see that it has the same schema as our global graph. It may be distributed a little bit differently, but these globe icons indicate that these elements of the schema are part of the global schema as well. Now that the graph is created, we can reconnect to the graph specifically within our TigerGraph solution. So what we'll want to do is set our graph name. And if you'll remember, we called it medgraph. And we'll just set that within our connection.graphName equals graph name. And then additionally, we will need to create a secret within our graph. So we'll create a secret, and we will use that secret to get a token that we can use for a secure connection to the graph. So we'll just go ahead and run that. And we'll get our token, which will allow us to now upload data and adjust things on the actual graph itself. So speaking of data, let's take a look at how we load in data, and let's grab our data. we're going to clone in our data from a GitHub repo, and I've already got it cloned. That's why it's giving us an error. But if we take a look at that data folder, so it's called Synthea Medgraph, we can open that up. And if we look at our data section here, we can see that we have all of our data files, and they also have a separate header file. So if we take a look at one of these, so this one is for devices, start, stop, patient encounter, code, description, and UDI. And if we were to look at the actual CSV file, we would see data that corresponds to that, start, stop, and so forth, the type of device. So that's a general idea of what most of our CSV files will look like. Things like patients will have quite a few columns, but it should be fairly easy to navigate these files. Take a look at these files in our notebook as well. So here is the header for our allergies file and the first 3 rows of data. So now let's take a look at how that corresponds to our loading jobs. So we need to create loading jobs before we can load in data. And loading jobs just define the mapping of these different columns within our data files to the different attributes of our vertices and edges. Let's take a look at how that actually works. Once again, we're using a GSQL block from pyTigerGraph. We're setting our graph. We need this begin and end statement when we're creating a loading job, just because otherwise pyTigerGraph will try to execute each line of this query as an individual query. So by just padding it with begin and end, we're saying everything in here is one query. Once again, we have create, and this time we are creating a loading job. It is called load allergies, and it is for our graph medgraph. This next line here is pretty important to take note of. So we are defining our file name, and file name is a variable type. So we're defining a file name variable, and we're calling it F1. And this is important because later, when we go to run this loading job, we'll be asked what variable we are trying to load in our file as. So we'll just need to remember that that is, in this case, that is F1. So when we go to load it in later, we'll say load this in as the variable F1. This next line here says load F1. So once again, load this file name variable called F1. And we are loading it into a couple different vertices and edges. So we'll see that we're loading it into our allergies vertex, which is good because that's our allergies file. And that our values, so the values that we're loading everything into. And then we'll see these $ signs and numbers. And that might be a little confusing at first, but those just correspond to the column number of our file. So if we look at, for example, our allergies file again, here's our header, ID, start, stop, patient, encounter code, description. And if we look at that down here and we just break that out, we see how each one of these $ numbers sort of corresponds to each of those columns. So our ID is our column 0, or start is column 1, stop is column 2, and so on and so forth. So here we can see that our first value is always our primary ID. Remember from when we created our vertex, that first value is always the primary ID. So our primary ID is our ID column. Here we have the allergy code, and then the allergy description, and the start and stop dates. Additionally, we can see that we're loading in this information to STOMED codes. So we're adding in those values as well to those vertices. And lastly, we're creating some edges. And if you remember, our first value in our edge is the from vertex, and the second one is the to vertex. So these will be the primary IDs of those vertices that you'll be linking to. So in this example, so here, patient has allergy values. We are starting at, if we look back up here, we can see patient has allergy, and that's coming from an allergy vertex and going to a patient vertex. So if we scroll back to our job, we can see that we're going from the ID of our allergy, and we're going to column 3, which is our patient ID. So that's what those look like. And then we can just specify some additional parameters down here that we have a header and that the separators in our file are commas. And that's it. That's what a loading job looks like. So you can load in any number of different vertex or edge types in one loading job. So let's go ahead and just run these loading jobs to create them on our graph. So if we run this, we will see that the loading job load allergies has been created. And we'll just go through here and run the rest of these loading jobs as well. There's quite a few of them, so we can just shift tab to run these cells and move on to the next one. And once those finish, we can get on to actually loading in our data. Now that the loading jobs are created, it's time to actually load in our data. Let's take a look at what that looks like. The first thing that we need to do is specify our file address. So we do that just by loading in the path as a variable. So we can see here that content is the root folder of your particular Google Colab instance. So that may differ depending on what Jupyter environment you're using or how you're running this. But otherwise, the structure will be Synthea medgraph data and then our data file. So we specify that that is our file path. And then down here, we use our connection. So this is one of our pyTigerGraph functions, upload file. And the inputs to that function are first our file path. So we can feed that in there. And then we have our file tag. If you remember from earlier, that is this file name variable. So it's F1 in all of our loading jobs. And we just need to specify that that is F1. You can load in multiple files in one loading job. So that's why that exists as a variable. You could potentially point multiple files at this loading job. But for the sake, we're going to only use one for all of our loading jobs, and we'll just reference that as such. And then lastly, we just need to specify the name of the loading job that we are running this file through. So this is our patient's file. We're loading it into the load patient load job. And if we go ahead and run that, we will see a big output. And that will just show us some statistics on what we've loaded. So it will say that our patient's file has 496 valid lines. So we have 496 patients. And then because that patient's loading job also creates the vertices for gender, race, ethnicity, patient address, we will see individual stats for each one of those. We say that those all created 496 valid objects. And then lastly, we will see the edges that we created. We can just go ahead now and load in all of these files. So once again, you could go a little crazy with Shift Tab through there. And these will each spit out a big output with stats of the loading job. So it'll get a little cluttered, but at any point you can just close these and minimize things down on themselves. All right, so that is everything loaded. We can see our last loading job here. It's all wrapped up. And we can verify that from pyTigerGraph. So anything that you can do through this Graph Studio interface, you can do through pyTigerGraph. So earlier when I was looking at the schema through Graph Studio, I could have sent a pyTigerGraph get schema call to return the schema to me from here as well. So for here, I'm going to run get vertex count. And here we have to specify that that is for stars, just wildcard, that's any type of vertex. And then for edges, we just get edge count, and we can leave that one blank, and it will by default select all of our edges. Our vertex count for each type of our vertices, we can see the total number that exist within our graph, and the same for our edges. Next, we can get some stats on a particular type of vertex. So any vertex type that has a numerical value to it will automatically have stats available on that. So those stats are the minimum value, the maximum value, and the average across all of the loaded vertices of that type. This also applies to edges as well. You can get it for edge attributes as well. So for example, we are going to run it on our patient vertex type, and we'll see that it has 3 attributes, which are numerical in nature and therefore can have statistics for them. So the birthday, these are expressed in epoch time. And then we can also look at our healthcare expenses across each one of these patients. So our average is frighteningly high, but that is merely the data. And then additionally, the maximum and average actual healthcare coverage that that patient has. So that's just how you get some basic statistics. Anything that you can do here with these vertices, vertex statistics, you could do with edges as well. Now, if we wanted to take a look at one particular vertex, sort of any type, we can do that. We can query it in the graph and take a look at its attributes, contents, and some other information about the vertex as well. And one of the nice things that pyTigerGraph can do is it can output results directly as pandas data frames. So here, this getVertexDataFrame function is going to output its results as a pandas data frame. So we're going to get a vertex of type patient, and this limit clause here will only return one vertex type patient. So if we run this, we'll see our pandas output is broken into multiple lines, but more or less each one of these is a column or an attribute in our vertex. So the VID is the unique vertex identifier. That's something that is really only exists in the graph and we won't really use, but here's our primary ID, our patient ID. Last name, first name, maiden name, there's no value for, that's just an empty string. Birthday, date time that they were born at, a fake SSN number, and so on and so forth. So those are all of the attributes that exist within our patient. And we could change this at any point for provider, I believe is one of our providers. There we go. And we can see that our provider's vertex has, once again, a unique VID. So every vertex type will have that field. Provider ID is its primary ID, and then name, utilization, and specialty are the three attributes of that vertex. Now that the schema is created, the loading jobs are created, the data is loaded, and we verified that it's in the graph, we can start writing some queries. Queries will allow us to explore our data in really an unlimited capacity. There's some really neat things that we can do with queries and some really cool ways that we can use them to look at our data in a way that you're just not able to with a traditional relational database. We'll start off small here, and then we'll get into some of the bigger stuff, but I'll walk you through a basic query, and then we'll get on to some more complex ones. Once again, we have our good friend, the GSQL block here. We specify that we are using graph medgraph, and we're creating a query called getPatientConditions. So this query is going to take an input of a first name and a last name, and those will correspond to a patient, and it's going to return a list of all the conditions that that patient has. So there is an edge called patient has conditions, and we're going to traverse that edge and return all the conditions that are connected to our particular input patient. Now what that looks like in terms of our query is we first declare that we have our two inputs, so they're of type string, and then their variable names are first name and last name. Any select statement that we have has to start with a vertex set. So in order to create a vertex set, we need to use one of these statements here. So here we are saying that our vertex set is going to be called seed, and it's going to be equal to all of our patient vertices. Within these curly braces specifies what is going to be within that vertex set. And here we are saying patient.star. So all vertices of type patient is basically what that says. So this vertex set is going to contain all of our patient vertices. And what that allows us to do is in our select statement, select S from seed. So seed is our vertex set, and then colon S. What this is doing is saying that for the duration of this query, we are going to reference our starting vertex as S. So this will iterate through every single vertex within that vertex set. And when it is iterating through, we can refer to the current vertex that it is iterating through as S. So we're going to select S, select the current vertex, where s.lastName is equal to our input last name, and s.firstName is also equal to our input first name. So this dot last name is an attribute within our patient vertex. So you refer to attributes within vertices with this dot here. So s dot last name for our current patient vertex that we are iterating through is their last name attribute equal to the input string last name that we have for our query. And if it is, then that particular vertex will be added to another vertex set that we will call patient. So ideally, this patient vertex set will only have one vertex in it, and that will be the patient that we're selecting. I say ideally just because TigerGraph doesn't know when you are writing this query that you're only selecting one vertex. It always assumes that there can be however many vertices in that vertex set. So that's why there's no real way to select just a single vertex, why we have to declare everything as these vertex sets, because through the duration of our query running, we have no way beforehand to really check all the data in our graph to make sure that running this query, I am not a robot, that running this query will only return one vertex. So everything will be a vertex set, even if it only contains one vertex. Next, what we're going to do is another select statement. And the select statement is from patient. So this is ideally our one vertex that we've selected. That is our patient with matching first and last name to our input. We're going to call that S. And then here we are traversing an edge. So this dash and then these parentheses in here specify the edge name. So these dashes would be on either side. And within the parentheses is the name of the edge. So we're traversing the edge patient has condition. And we'll see that we're also assigning a variable to that edge for the duration of this query. You don't have to. If you see here, we're not referencing that anywhere. So we could get away with this, no problem. But if you wanted to reference that, you could specify it as well. And then lastly, afterwards, we have the destination vertex type that we are going to. So we are navigating from our patient vertex, which is of type patient, through the edge patient has condition, and we are going to a vertex of type conditions. And we're calling that C. And we're selecting C. So we're selecting any conditions that have edges that connect them to our input patient, and we're storing that in this response vertex set. And then lastly, we just print our patient. So this will print that patient vertex set, and we will print response, which will print this response vertex set as well. So when printing these vertex sets like this, when printing them, it will print not only all of the vertices within it, but it will print their attributes as well. So we'll get a full readout on all of the vertices within that set. And running this block will save the query to the server. Now, the thing to note here is that this query has been saved to the server. It has not been installed. So there's a difference between a saved query and an installed query. But long story short, to run a query from one of the built-in query endpoints. So when you install a query, it creates a REST endpoint for that query. And in order for us to run that query from pyTigerGraph, we need to have that REST endpoint. So in order to create that endpoint, we just need to install our query. And we can do that with this block of GSQL and the install query statement. One thing to note is that this query install will take a minute or two. Now we can see the query is installed 100%, and it is ready for us to be able to run. So running it, we have a pyTigerGraph function run installed query, which takes in the name of the query that we're running, and then a dictionary of the inputs for that query. So you'll always have the input name and then colon, and then the value of that input. So for this example, we're going to run the query that we just installed, get patient conditions, and we're going to use some of our example inputs here. I got these inputs just by pulling them out of the patients file. So I just opened that up and I scrolled over to these names, and I was able to just go through and grab a couple to sample out. So that's how you can get some more names if you don't want to use any of the ones here. But running this will give us the output of our query. So if you remember, we are outputting the patient vertex set. So we'll see that this is a list because it could contain multiple vertices. And then within that, we have a JSON structure representing each vertex. So we have that unique vertex ID. The vertex type is a patient. We have the first and last name because those match what our input was. And then we have the rest of the information about that patient. Additionally, in our response variable here, you'll remember that we returned all of the conditions that were related to that patient. And we'll see here that we have a bunch of vertices of type condition, and we can see what type of conditions those are on our person. So that's a basic query to just do one hop out from a person and get something connected to them over an edge. Next, we'll explore a multi-hop traversal. For this next query, we're going to return all of the SNOMED codes related to a patient. If you remember, looking back at our schema, SNOMED code doesn't directly attach to patient. So in order to get to SNOMED code, we're going to go through another vertex that's attached to it, and then from there, back out to the SNOMED code. So let's take a look at what that looks like. The first bit of our query will look very similar to our previous query. We're taking in a first name and a last name as an input, and we are setting an initial seed variable as all of our patients. And then from that seed variable, we are selecting the patient that matches our first and last name. One thing to note here, though, is that at the end of where we have foregraph, medgraph, before that was just the end of our declaration, but here we have specified syntax v2. Multi-hop traversals require syntax v2, so we just need to specify that we want to use that syntax in our create statement, so that way we can actually use it within our query. Now, speaking of multi-hops, this select statement looks a little funny, so let's go through what that's doing. So once again, we are selecting C from patient is once again that vertex set containing only our matching patient. And then we're going through an edge of unspecified type. So what that means is we will go through any edge to that patient, and that leads to any type of vertex. So we see here that we have nothing before our colon and vertex, so that's just saying wildcard any type of vertex. And then from there, we're going through any type of edge as long as it ends up at a SNOMED code vertex. So let's go back to our schema just so we can more easily visualize what that's doing. So here we have a patient, and we have a bunch of edges connected to patient. And for a lot of those edges, they lead to vertices that are then connected to SNOMED code down here. But for some of them, they're not. So within our query, we specified that we only want to traverse edges that come out of patient and then go to a vertex and then go across any edge type that leads to SNOMED code. So because of that, we're not going to traverse any of these edges to any of these vertices because they don't follow that specific pattern that we're looking for of any type of edge, any type of vertex, any type of edge, SNOMED code. So that's just what that pattern here is saying. Start at our patient, any type of edge, any type of vertex, any type of edge, SNOMED code. And that SNOMED code is C, and that's just what we're selecting. And this query will just, like our last one, print out the patient and their information. And additionally, it will print out that vertex set containing the codes and all of the information as well. So we'll just go ahead and install that query and wait for that to do its thing. And then we can run it once it's installed. The query is installed. So let's take a look at running it. Once again, list of sample names. You can get more names from the patients file. We're using Colbert this time. We will run it. At the top of our return, we have the patient. And once again, we have our matching name and the rest of their information. And then here we have a list of SNOMED codes And within those, we can see that they contain a description as their attribute as well. So we can get an idea of some of the medical interactions that our patient Cole has been through. Now that we have the basics of how to do that type of stuff, let's take a look at some more advanced things we can do to build off of that. So this next query is going to take a similar approach where we're working off of SNOMED codes. And for any given SNOMED code, we're going to find an attached vertex, which contains a cost. So looking at our schema, we see that immunizations have a base cost attribute, as do procedures and medication. So those are the three vertices that we'll be caring about to get that base cost from. And we can see here our input is a vertex SNOMED code. So this input is going to be the primary ID of a vertex of type SNOMED code. So I have some examples listed out there, but once again, you could see this by going into the procedures file, which is too large to see, but you can get ahead of that procedures file and you could pull out some of the SNOMED codes from there. We're declaring an average accumulator. So what an accumulator does is for each one of those iterations or for each one of those vertices that you're iterating through in a select statement, it executes some sort of functionality per iteration. So in the case of an average accumulator, you can add a value to it. And what that will do is average it with all of the previous values that have been added to that average accumulator. So the value starts at 0. And as you start adding more values in, they will be averaged out with each other. So what we're going to do with that average accumulator is we're going to populate it with the cost of any of those types of medications, procedures, or immunizations that are connected to our input SNOMED code. We first need to convert our input vertex. So our input vertex is called encode. We first need to convert that into a vertex set so that way we can use it in a select statement. Just like we were doing before when we were wildcard selecting all patients of one type, what we can do is just take that input, we can put it within curly braces, and that will now create a vertex set out of it. And that vertex set will be named code. So our select statement will originate at our code, our input SNOMED code. It will traverse through the edge medication code or the edge procedure code or the edge immunization code. So these pipes between our edge types just signify that it can be any of these edge types. So you could potentially specifically list out as many or as few edge types as you want. And then we were saying land on whatever vertex is on the other side of that edge. So because I specifically listed out the edges here, I don't also need to specifically list out the vertex types because those edges only lead to their corresponding destination vertex type. So that is variable p, and that's what I will be selecting. And then down here, we have an accum block, which basically says we're going to put an accumulator in here, and that accumulator is our average cost accumulator. And for each one of these p vertices that we iterate through in our select statement, we are going to take the attribute base cost and we're going to add it to the average accumulator. So what this will essentially do is give us the average cost of any particular healthcare system encounter related to our input SNOMED code. Let's go ahead and install that. Query is installed. Go ahead and run it. Once again, I've included a list of SNOMED codes here. And we can see that the average cost for medication reconciliation is $506. We could grab any one of these and paste that code in there and run that again to get the average cost of having a wound stitch closed, $9,000. Now that we have the average cost of these codes, we can start looking for outliers there, anomalies or things that may be suspicious or potentially even fraudulent activity. So what we'll do is we'll try to find any particular interactions where their base cost is significantly above the average cost for that particular code. So to take a look at what we'll be doing, our input will again be a vertex of type SNOMED code. So that's the code that we're starting at. And then we also have a float, which will be our threshold value here. So we are using this threshold to only select codes that are 90% greater than the average value. So close to double the cost of the average procedure. What we're doing here is we are setting a double average cost to the output of our previous query. So we are calling our previous query get code cost. We're calling it within this query. So it's essentially a subquery within this query now. And we're feeding it our input code vertex type. And then that's just giving us that average cost that we were getting from running the query before. Next, we're going to select our code. And we're going to do the same step that we did in the get code cost query to traverse those three edge types to get to our vertices that have that base cost attribute. And we are going to select any of those vertices where the base cost is greater than our average cost and our threshold. And we're going to accumulate those into a map-accum. So a map-accum is basically a key value pair. And our key here is the vertex ID, so the vertex of the type that we're selecting. And the value is the cost, so that base cost. What this accumulator will end up with at the end of the statement is a key value pair where the key is the primary ID of a vertex and the value is the cost of that particular medical interaction. So we'll end up with a list of those key value pairs of that structure. And additionally, what we can do is we can order those values by base cost descending. Something to note is that this ordering will only apply to the vertex set here. It does not apply to our accumulator. And then here we will just print the average cost of our input. We will print out our accumulator, which has the IDs of each one of those costs and their actual cost. So these will be our ones that are more than 90% above our average. And as a return statement, this query will output that vertex set of payments. If we want to use those high value payments or high cost payments later on, query will return a set of those that we could use in a later query. Once again, we'll install this. Now that it's installed, we can run it just like any of our other queries. So we'll just paste in a value, we'll run it, and here we can see that the average cost of getting a wound sutured closed is $9,300 as we saw before, and our two high cost procedures cost $17,000 and $19,000 respectively. So those are definitely significantly above our average cost, and these are the vertex IDs of those particular interactions. So we can do that again with any of our other SNOMED IDs. This one only has one, it's above a particular cost. And this one we can see here that there are no procedures containing this SNOMED code that were 90% greater than the average cost. So our return here is empty. If we were to adjust our threshold, might have to go even lower. There we go. Then we can start seeing some that satisfy those requirements. For this next query, we will once again build off of our previous two queries, and we will really pull together some of the power of graph here. What we'll attempt to do is using those outlier interactions that we identified in the previous query, attempt to recognize any providers who have a high percentage of high cost interactions versus regular cost interactions. Let's dive into the query. It'll be a little bit easier to understand there. We'll see that this query has no inputs because we're going to run it over every single SNOMED code that is loaded into the graph. And we'll see that we're doing that here. Codes is our vertex set for all of our SNOMED codes. We're going to select all of our codes. Within our accumulate statement, we're going to run get cost outliers as a subquery. the input to that query will be the actual SNOMED code vertex, and then we're specifying our threshold of 0.9. This will take all of the codes in our graph, run them through that subquery that we wrote up here, which will then return any interactions where their base cost is 90% higher than the average for that interaction. And all of those will get lumped together into this vertex set accumulator called high cost actions. Next, high cost actions will get converted into a vertex set so that it can be used within our select statement. And this select statement is going to identify the providers that are tied to these high cost actions. So we're selecting P from actions, that's our high cost actions. We're traversing through any edge type to an encounter vertex. And then from there, we're traversing through the encounter has provider edge type, and we're landing on a provider, which is labeled P, and that's what we're selecting. Within there, there's an accumulate statement where we have a vertex attached accumulator. So when we have two @ signs, that's a global accumulator, and it exists within the scope of the query. But when we only have one @ symbol, that signifies a vertex attached accumulator. So this accumulator is attached to this particular instance of P. Every provider that we cycle through in this select statement will have a pseudo attribute added to it for the duration of this query. And that attribute will be called @highCost, and it is of type SumAccum. So this is a sum accumulator. And what we're doing here is we're adding 1 to it. So for every high cost action that is linked to a provider, we are adding 1 to the count of high costs that provider has. So that particular provider will have that high cost vertex attached accumulator, and we're adding 1 for every high cost action related to that provider. Additionally, this post-accum statement, so after this accumulator has run through, after we've run through every single provider, we're then going to run through them again, and we're going to say, create another vertex attached accumulator, another SumAccum type float, and we'll use this outDegree statement here. So what this does is gets edges that are connected to this current vertex. So outDegree will get any edge that is connected to that vertex, but by specifying an input to outDegree, so here we specify encounter has provider, we say we only want to count edges of that type. So this will output the number of encounter has provider edges that are connected to this particular instance of P. And that will get stored in that vertex attached accumulator edges, which is also tied to that same P vertex. So what these edges represent are the number of interactions that that provider has had, and we'll use that to compare it to the number of high cost interactions. So that's what this next line does here, is it takes that provider's number of high cost interactions and divides it by the total number of interactions that provider has had in order to give us a percentage of high cost interactions. And that will once again be stored as a vertex attached accumulator. So now whenever we reference any of those providers' vertices within this query, we'll be able to get the value or add to the value of that percentage high vertex attached accumulator. And that's exactly what we'll do in this next select statement. So we'll select P from our high cost providers. That's the output of our previous select statement, where the number of edges, so the number of total interactions, is greater than 10. This is just to filter out maybe, a provider's only had 4 interactions. They've all been high cost. That'd be 100%, but that's not really data that we should be considering in this. So we're going to filter it to only providers who have had more than 10 interactions. And then additionally, we're going to order the results of this query by their percentage of high cost interactions. That's going to be descending. So our highest value will be at the top, going down, and then limit that to only the 10 highest percentage providers. The vertex set here, top providers, will only contain at a maximum of 10 providers. And then lastly, we would just print top providers. We can go ahead and run that query now. You'll see we don't need any inputs here because there are no inputs for the query. So we can just say run installed query and then the query name. And here's the output of our query. So this is the top provider's vertex set. There should be at a maximum 10 providers in here. And we'll see that they have their percent high vertex attached accumulator and the value of that. So this provider has 27 total interactions, and of those, 8 of them were high cost, which is roughly 30%. So we can go through here and we can see the other providers that returned high values as well. So this is by no means, a conclusive, oh, that must be fraud type scenario. There's obviously more you would need to take into account here. You could look at things like the demographics of the people who those providers served. Some of them may be in higher end areas or larger cities where costs might be higher. So that could factor into those unusually high payments. There could be other scenarios such as related SNOMED codes to those particular procedures. So it could be something like a basic procedure, but there's a complication, and there's also a code for that complication related to that procedure as well that could cause it to be higher cost. So that would be something to look into as well. But this query provides a great jumping off point for diving further into that information, or even just taking the output of this query and jumping into Graph Studio and doing a little bit of digging around directly into some of those providers to see how they could connect to each other. So you could do something like that by, let's just take, for example, a couple of these providers. So provider ID, just copy that. Vertex type, providers, paste. There's that provider, and we'll grab another one just to see if we can find anything here. Grab. Just expand these out by double clicking on them. And then we can rearrange our graph. And immediately those don't have anything that connect them, but we may be able to expand out further using expand from vertices. Selecting our 2 starting points. And if we rearrange this, we can now see that these 2 providers aren't very connected to each other. There's a couple connections here between payers that serviced their interactions, but otherwise it's not a very densely connected graph, at least not with this number of traversals. But anyway, that's just kind of an idea of some poking around that you could do just with the results of a query like this and some graph traversals. Next, we're going to take a look at another type of insight that we can gain with graph queries, and that is similarity. So we have a bunch of patients, and we have a bunch of demographic information about them, and we have their history of interactions. How can we use all of that to find patients who are similar to each other? So additionally, we have some location information, and we want to run distance calculations on that. So our location information is in the form of latitude and longitude coordinates, and we need to find a way to turn that into a distance that we can then reasonably use to determine how far away people are from each other. So this is just a subquery called check distance. We're never really going to run this query on its own. It's purely meant to be run from our next query. But what it does is it takes in a vertex of type address and then a latitude and a longitude, both in form of doubles. So those would be coming from our input patient, and this would be an address that we're checking against. And it does the Haver-Sign formula to calculate the distance between those 2 points on a sphere. So that's some math. You can click this link to look into what's actually going on there. But one thing I do want to note is that we have print statements within this subquery. But when we run this subquery from our main query, those print statements will not print in our main query. So if you're looking to get output out of a subquery into your main query or have it print within your main query, then you will need to return that information. Printing it will not print when being run as a subquery. So that's just something to keep in mind as you're kind of nesting queries together if you start doing that with your graph build out. So lastly, let's take a look at the actual similarity query. So our inputs for this query are once again going to be a first name and a last name, just like with some of our previous queries, and additionally a integer number of how many of our top matches we want to return. So just like we were limiting in our previous query to only return the 10 providers with the highest high cost percentage, here we're saying that we only want to return top K number of matches. All of this will be pretty similar to what we do in our previous queries, just a bit more of it. This looks like a lot, but realistically, a lot of these select statements are very similar to each other because they're doing similar things just along different edges or vertices that have different attribute names. So they can't all be done from within one select statement. But these first couple blocks are just starting with all of our patients, getting their gender, which we're storing in a vertex attached accumulator. And we're also getting their birthday that's stored on the vertex, and we're comparing that to now. These functions here, year and now, are GSQL date functions. We have a link here where you can see some more of those, but basically what these are doing, year is extracting the year from the datetime attribute birthday. And then once again, this year function is extracting the year from now. Now is just the current date time that this query is being executed at. So it's taking the current date time, it's taking the 2 years, the year of its current year, 2021 is time of recording, and the year of the birthday of our input person, and it's subtracting them just to get their age. Once again, stored as a vertex attached accumulator. These next couple select statements do pretty much the same thing, just with collecting the race, the ethnicity, and the latitude and longitude that the patient lives at. So just a single hop traversal across those corresponding edges to those corresponding vertices. Then we print out the patient's vertex set, which should only contain our matched patient because that's what we're setting it as. Patients is where last name matches last name and first name matches first name. So this is our input patient, and we are printing out specifically their last name, first name, ID, and our vertex attached accumulators that we created for their location and other attributes. These next select statements correspond to the entire population. So this top half is just getting the information for our input patient, and this bottom half is doing pretty much exactly the same thing except for the entire population. So what it's doing is grabbing anyone that doesn't have the same ID as our input patient, and then getting, once again, their age, tying that age to that particular patient. And then here we have an if statement, or we're just comparing the age to our patient's age, and we're dividing them just to get a number between 0 and 1 that we can use for the comparison later on. All of the numbers used in the comparison will be between 0 and 1, 0 being no match if we're doing a binary comparison where something like gender, are they of that gender? They're either of that gender or they're not of that gender, so it's either a 1 or a 0. But where things like age will represent that as a number between 1 and 0, a double in these cases. So once again, do that with age, race, sex, ethnicity, and then down here is where we use the check distance subquery to check the distance between the input patient and the particular patient that we're referencing them against. And then lastly, down here is the actual similarity calculation. So it's just taking those accumulators, which hold that value between 0 and 1 for each one of our comparison points, and we just add all of those together and divide it by 6 to get the average difference of those 6 properties from our input patient. Go ahead and install that, and then we can run it to see what that gives us for an output for some of those patients that we had from before. Query's installed. We can go ahead and run it with some of our sample inputs. So we'll be using Cole Bayer again, and we'll be returning the top 10 people who are similar to him. Here we have our input patient and his results, and the most similar patients. So we can actually see that we have a couple of patients that are identical, represented by the infinity, and the rest of these are relatively similar. We can try it with one of our other inputs. And see those results as well. So this can be used for community detection or building communities. You could write a query that could easily traverse through all of the people, find their similarity across other people, give them a score for each person that they're related to, and use that to build out a community in the graph as well. And there's plenty of things that you can sort of use these queries as a base for to build upon and extract some more information out of the data in the graph. So I hope you enjoyed taking a look at TigerGraph within the healthcare space, and hopefully it inspired you to want to give this a shot, try out the notebook and spin something up for yourself. Maybe try your hand at writing a query, see what type of insights you can gain on your own or build off of any of the queries already written here. And don't forget to check out our documentation and our community. We have a great Discord community and a very friendly forum community who are always happy to answer any questions or try and help you out with any TigerGraph projects that you might be working on. So remember to check those out, and there will be links in the description for all of those. I hope you enjoyed and have a good one.